Good afternoon. So we will proceed exactly like what we did yesterday. One of the things that I am trying to do in this video lecturing is, so let us go to the slide. First slide is talking about yesterday's doubts and clarifications. We call it minute paper, which says that there were some questions about that sensing of mercury ions by the oligonucleotide. So yesterday what we have discussed is a method of developing a sensor for water purification using gold nanoparticle. So gold nanoparticle was used and there was a color change as a result of binding of mercury. But many colleges say that that mechanism is not clear. Why mercury alone is identified? The pollutant water may contains many metal ions. Why mercury alone is collected? And what is this nucleotide doing there? And the last college also detection of mercury oligonucleotide. So which means that basically the mechanism of detection was not very clear. So we will discuss that part today before we move to the next spectroscopic technique. So AU nanoparticle based detection, that is what yesterday's topic. So imagine that there are several gold nanoparticles which can absorb, and one of the things that we yesterday told, the reason why they selected AU nanoparticle is that it has high molar extinction coefficient. So this absorb at a wavelength of 520 nanometer is the visible region, right. So what they did is they use a single strand DNA. So DNA is usually double strand, but they have selected single strand. So we can prepare single strand as well as double stranded DNAs. They use one oligonucleotide with a specific distance or length. That's the structure that I have shown you yesterday. So that particular oligonucleotide you can bind with a gold nanoparticle. All that you need to do is mix it, because oligonucleotide or the single strand DNA unit has a negative charge, phosphate unit. So that can attach to the gold nanoparticle surface, and they will be attached to the surface of each of this nanoparticle. As a result, there will be a double layer formation. That means any of this capping agent or any species that is attached to the gold nanoparticle, because of the electrostatic interaction, there will be some surface charge development. Okay, so this surface charge, it can be either negative or positive. So depends upon the capping agent, it can be either positive or negative. Whatever may be the charge, because there will be same charge on each nanoparticle, they don't come close, they repel each other. Now suppose you are adding mercury ions. Mercury ions also start interacting with the gold nanoparticle or on the surface. Now the surface of gold nanoparticle already has this single strand DNA, and because mercury can interact with this particular single strand DNA much better than the gold nanoparticle, what happens is that single strand DNA become double strand through the interaction of mercury. So basically each of the single strand or the single strand on the gold nanoparticle, they becomes double strand by interacting through the mercury. This dot is nothing but mercury. So what happened then? There will be a reduction of the surface charge on the gold nanoparticle, and so that they can come close to each other and they aggregate. Or in other words, you will get a bigger nanoparticle. And we know that as the size of the gold nanoparticle changes, its absorption changes. We know that is a function of the size of the nanoparticle. So since because of this stripping of this nucleotide by mercury, it so happened that you are facilitating the aggregation process of gold nanoparticle. And as a result of aggregation, the size changes and absorption changes. So initially we will have a 520 nanometer absorption. So what color the solution will be? If the species absorb 520 nanometer, what will be the color of the solution? Can you guess the color of the solution when the species absorb at 520 nanometer? The absorption spectrum is given like this. This is wavelength, this is absorbance. So this is 520. So I want to take 1 minute. Think what will be the solution color if it absorb at 520. Can any one of you tell what will be the color of the solution if absorption is at 520? Yellow color. Yes. So that's the answer. If it absorb this color, that color won't be seen. So whatever color is absorbed, the remaining color is what is coming out. So you'll have an yellow color. But upon binding the mercury, what happens is that this absorption shifted to the yellow region. So now this color which is not absorbed will be given out. So it will be bluish green. So because of this particular process of aggregation of nanoparticle, there is a color change from absorption band changes from 520 to probably 670 or 700, and as a result the intensity of the outgoing light changes from yellow color to a greenish or bluish color. So this is the technology, or this is the principle that they have utilized for detecting mercury. Now the question is why only mercury? There can be several toxic metal ions present in the system. Why only mercury is bind? That is because the type of interaction. They are facilitating thymine mercury thymine interaction. So the bond strength or the bond energy of this kind of interaction is much favored compared to any other metal. So they have checked for zinc, calcium, many divalent ions. In fact, I have shown you that graph yesterday. Many divalent ions they have checked, but none of them match with this interaction. That's the reason why this particular experiment was more specific towards mercury. So I hope that one is clear now. Now we'll go to the slide again. There were some questions. Yeah, the one question is how the optical density depend on wavelength. That's a good question. If you look at the UV visible spectrum of any compound, for example, let's go to the board again. So you must have seen the absorption spectrum, absorbance versus wavelength, sometimes like this. So as the wavelength changes, you will have different absorption. That's a question that is asked, how the optical density or absorbance is depending upon the wavelength. The answer is they are connected through the molar extinction coefficient. Even though the Beer-Lambert's law is A is equal to epsilon Cl, where lambda is not coming in this equation. But what happened is that in every lambda, for this can be 200, this can be 300, this can be 400, every lambda the molecules can have a different epsilon. So epsilon is, it depends upon the type of molecule and also on the lambda. So what kind of molecule you are using and what wavelength you are dealing with depends upon these two parameters. Epsilon can change. In other words, epsilon is a measure of to what extent the electronic absorption takes place. There is a technical term called oscillator strength. Okay, so you can actually calculate by calculating transition dipole moment using some quantum mechanical equations, which will tell you what is the strength of that absorption. So that strength will tell you how much of your absorbance you are getting. Sometimes you will have high, sometimes you will have low, depends upon the dipole orientation. Yesterday I told you in a very brief manner that the dipole orientation of these molecules and the incoming radiation interaction, that is the one that determines the epsilon. So some lambda, this is a favorable orientation, there you will get a much more high absorption, some case it will not. So the lambda is connected with absorbance through the epsilon value. There was another question, why is transmittant has a log value and absorbance doesn't have a log value? We have find out a relation between absorbance and transmittance yesterday. So in fact the definition says only absorbance has log value. Absorbance is defined as log I0 by I, and transmittance is defined as I by I0. So all that you can do is you just substitute T here. This is basically 1 by T. So we will get a relation between A and T. In actual sense, A is a logarithmic function, but T is not. Third question is concentration and intensity. That's not a question, that's a statement. I'm just guessing the relation of between concentration and intensity is what is asked. So as you can see, they are directly proportional. The absorbance and concentration are directly proportional. That is why when you plot Beer-Lambert's plot like absorbance versus concentration, you get a straight line. They are directly proportional. After a particular concentration, very high concentration, probably deviation will happen from the linear nature. That is not because this law is, this Beer-Lambert's law is incorrect. That is because there are some other things can happen in a solution, such as aggregation. So the molecules can aggregate at higher concentration, and aggregation can as we see in the gold nanoparticle, aggregation can change the color. So the lambda may change, and when lambda changes, epsilon changes. So then whole spectra will change. That's the reason why the absorbance and the concentration plot changes from the linearity. But concentration in general is proportional to the absorbance. Okay, so that is all about yesterday's class. We'll go back to the slides now. We are continuing with the spectroscopy and its applications, and today's topic is fluorescence spectroscopy. It is another spectroscopic technique with a lot of applications and sensitivity, because one of the things about fluorescence spectroscopy, why engineers are interested in fluorescence spectroscopy based technique, is that you don't need much of a sample to analyze. It can works with nanomolar concentration, 10 to the power of -9 molar concentration. It's highly sensitive technique. There is one book that is author is Lakovis, Joseph Lakovis, and the title of the book is called Principles of Fluorescence Spectroscopy. So majority of the things that a student needs to know about fluorescence spectroscopy is available in this particular textbook. So these are the intended learning outcomes that we are planning today. At the end of this session, you should be able to explain the basic concepts of photophysical processes. What happens when a molecule absorbs light? What are the photophysical properties that happen in a system? And how can you develop a fluorescence based sensor for detecting toxic metal ions? Similarly, what we have done yesterday were a UV visible based sensor for water purification. We can also think of developing a sensor for water purification using fluorescence spectroscopic technique. Okay, so this is a slide that I have shown you yesterday. What happens when a molecule is getting excited with the different types of electrons? It has sigma electrons, pi electrons, and non-bonding electrons, as you can see in the highest occupied molecular orbitals, and non-bonding electrons like pi star and sigma star. So when electronic transition happens from HOMO to LUMO, you can have N to pi star, you can have N to sigma star, you can have pi to pi star, pi to sigma star, then sigma to pi star, and sigma to sigma star. So yesterday we briefly mentioned this. When a system with the 2 electrons in its ground state, when you excite that, it can go to, one of the electrons can go to the excited state. Okay, so an interesting question can come, why 2 electrons are not going? So one of the things that I want you to think about is keep asking questions, why this happens like this, why can't it happen the other way? So usually one electron is going up to the excited state. Now as soon as it reaches there, its spin remains the same as in the ground state. So initially they are paired. So that is because Pauli's exclusion principle suggests that any orbital, if there are two electrons, their spins have to be paired, otherwise stability is not sorry, it's not stable. So the moment you excite, look at that spin, it is the same thing as in the ground state. But the question comes, as long as it stays there in the excited state, there is no other electron in the vicinity. So why does it keep the spin as the same? It can change its spin. So whether it changes the spin or not, it can lead to two different states. If it is changing the spin, you call it triplet state. If it is not changing the spin, it is called singlet. So we'll come to the details of why it is called singlet and why it is called triplet. So this kind of a diagram will try to tell you what is happening upon light absorption. So I will give you 1 minute to look at this slide, and then I will come to one college and request you to explain what you learned from this slide. You can talk to each other and try to explain the content of this slide.
Hello?
Yeah.
Yes.
Hello. Hearing you. Yeah.
Sir, it's Jablonski diagram, sir. It explains how fluorescence and phosphorescence takes place, the phenomenon of both these photoluminescence concepts. In fluorescence, the electron will, after its vibration, it will relax back immediately, but in phosphorescence, it won't re-emit immediately, it will take some time. So it will again spin change will be there, and afterwards it returns to ground state. From singlet state to, it will go to excited triplet state, and afterwards it emits energy and it again come to ground state.
Okay, so that's a reasonable good explanation. One more question I have is, in that slide, can you see that I'm showing there are two lines on the right hand side and one line on the left hand side, and there are two lines on the excited state, again two lines on the triplet state, singlet excited state as well as triplet excited state. So usually textbooks don't show like this. They will have only one line, there will be two electrons here and one electron going up, one electron come here, and it comes back. So what way this is different from the usual Jablonski diagram that you have seen? Can you come to the board? So I will explain to you that difference. So this is how it starts. Then there will be an excitation, one electron will be here, then it changes the spin, it comes back here. If it is coming back from here, it's called fluorescence. It is coming back here, it is called phosphorescence. This is the potential energy. This they call it S0, S1 and T1. And this basic structure is called Jablonski diagram, because Alexander Jablonski is the first person who introduced this diagram. But I am not representing exactly like this, a slight variation, because this is not really accurate. The best way to represent this diagram is S0, S1, T1. So what the difference between this and this is, S0 is an electronic state of the system. It is not only for these two electrons. Okay, S0 is the state of the whole molecule. Now in the molecule there will be several molecular orbitals. So on the right hand side is what is shown as the orbital picture. This is the electronic energy associated with the whole system. So when an electron absorb energy and then move from one orbital to another orbital, for example S to P, the electronic energy of the whole molecule changes. Okay, so this is S0 of the ground state of the molecule, and the whole molecule will go to S1. In this representation, the problem is one electron is still in the S0. If you see some kind of a notation like this in the textbook, that is wrong. Okay, so realize that the entire molecule is going up with the electronic energy. Only thing is there is an orbital separation of electrons, and then within this state there is something called inter-system crossing, ISC. That means, as we said, the spin of this electron can change because it is unpaired now. It is not connected. Here they are paired. Here they are separated, orbitally separated. So this electron is free to change its spin. So when it's free to change its spin, there can be a possibility of existence like this. Okay, that's the reason why it is called triplet. Now that's another state. Why it is called triplet? Why it is called singlet? That is another question. There might be some reason for choosing the names. So I want you to take 2 minutes and then tell me why this particular state is called singlet. Of course 0 is understandable, it's ground state, this is first excited state, so there can be S2, there can be S3, but why it is called S, why it is called T? It has something to do with the spin of the electron, obviously, but I want you to tell me that answer, why it is called singlet, why it is called triplet.
In singlet, electron states are paired. But in triplet, it has a spin orientation parallel with the different electrons.
Right.
So the name singlet and triplet.
But where is it actually coming, this singlet and triplet? What is the idea behind it? The only difference that you are seeing is, in one case, as you said, the electrons are paired. In other case, electrons are unpaired. So I mean, just from English language, singlet means single state, triplet means 3 states. Call it triplet. Triplet means 3, singlet means 1, doublets means 2. So all these words has its own meaning. So when you say singlet, there is only 1 state possible. Then when you say triplet, there are 3 states possible, even though we are showing only 1 there. So what are the other 2 states? And how do you say that there are 3 states? How do you say there is only 1 state? Let us go to the board again. So there is something called total spin multiplicity, which is given by the 2s plus 1, where s is the total spin. So when there are 2 electrons, when they are paired like this, one spin will be plus half, other spin will be minus half. So s is going to be 0. So when you apply 2s plus 1 rule, what you are going to get is only one value, sorry 1. 2s becomes 0 and 1. So only one value, that's why it's called singlet. So as long as the electron spins are paired, in this series you are getting only singlet states, S0 ground state, S1 first excited state, S2 second singlet state, excited state, and so on and so forth. So you are getting only singlet states. Whereas in the case of triplets, now you can have a chance of plus half, right? So you can have a value of 1. So if you put that 1 here, that answer is going to be 3 states, or there can be 3 as a value of the spin multiplicity. 3 orientation of spin is possible, that is a physical meaning. Either it can be both up or both down, or 1 up 1 down. So because of these 3 different types of orientations, there are 3 energy levels are possible here with this particular arrangement. That's why it's called triplet. So the basic photophysics understanding is very important to understand the terminologies, why it is called singlet, why it is called triplet. Okay, we'll go back to the slides again. So we call this as state energy diagram. So just now you are seeing again a state energy diagram, or you can call it as a simplified Jablonski diagram. There will be S0, 2 electrons, 1 electron get excited to S1, and it is still paired, the spins are paired. After, depends upon how much time it is going to stay there, it can undergo intersystem crossing, it comes to triplet state as you can see here, where the spins are parallel now. Now I have written here n pi star that is just an example. It can be n pi star, it can be pi star, it can be sigma to sigma star, any homo-LUMO transitions can be represented. If it is n to pi star transition, remember that formaldehyde molecule we were exciting a few slides back, and there was a transition of non-bonding electrons moving to the LUMO, so into a pi star orbital. So suppose that is a transition that we are talking about, then this singlet state is called n to pi star state. So it is an n to pi star singlet, and this state is the corresponding triplet is called triplet n to pi star. So now what I want you to do is I want you to draw a similar state energy diagram for a pi to pi star transition. So quickly 30 seconds you can take, draw a state energy diagram for pi to pi star transition.
Lyman's
Yeah.
Lyman, Bama, Pasture.
Oh, okay. Hold on. So those series, this emission series, you must have learnt in a hydrogen atom spectra. Lyman series, Balmer series, Paschen series, which are all emission lines. Okay, but I am talking about a particular different types of system where you can have, see, the Lyman series, Balmer series is for one electron system like hydrogen like atoms. In this particular case we are talking about a n to pi star and pi to pi star transition. Whatever spectra I have shown you is for n to pi star. Probably come back to the board, we'll discuss a bit more. So an organic molecule like ketone, okay, where there are pi electrons as well as non-bonding electrons. See, the oxygen has electrons which are not participating in any of the bonding, okay, and there are electrons which are participating in the bonding. I can excite two types of electrons in this particular case, the electrons which are participating in the bonding and electrons which are not participating in the bonding. My question was, how do you draw a Jablonski diagram representing these two different types of transitions? One I have shown you. So there is a ground state which is represented as S0. There will be an excited state which can be represented as S1. So suppose I am exciting these non-bonding electrons, it will be a n2 pi star singlet state, because non-bonding is going to the pi star anti-bonding. Remember this basic energy levels structure, you have sigma bond, pi bond, non-bonding electrons, and then this is pi star and sigma star. So this is called HOMO and this is called LUMO. This is called highest occupied molecular orbital, lowest unoccupied molecular orbital. This is the same picture as from the molecular orbital theory. When you have two atoms come together, the atomic orbitals combine to form molecular orbitals. That is something that you have learned in +2. So when you have this molecular orbital filled with electrons, upon getting the energy, they can jump to the unoccupied orbitals. So this transition happens if it is a lone pair or non-bonding electron, you call it singlet n to pi star, and it goes to a triplet, it is nothing but triplet n to pi star. So the question was, what will happen if I excite these electrons, pi electrons? And the answer is very simple. Instead of a singlet n to pi star, you will get a singlet pi to pi star energy level here, which undergoes intersystem crossing. Here he will have a triplet pi to pi star. So depends upon what type of electrons I am exciting, I can have both singlet state as well as triplet state electronic excited states. So let's go back to the slides again. So in some textbooks, photochemistry textbooks, if you see, they might have given notation like singlet n to pi star, singlet triplet n to pi star, which only means that the electronic transition involving is the n to pi star electronic transition. Now there is another question. This triplet state, many of you know about Jablonski diagram. This triplet state is always placed lower in energy than singlet state. There is no Jablonski diagram which shows a triplet state energy higher than that of a singlet state. What could be the reason? So I want to take a couple of minutes and then see. The only difference, as you know, these electrons are, the spins are paired, the spins are parallel. So why parallel spins will result in reduction in energy. So some colleges have written triplet is stable. That is obvious reason, triplet is stable, that's why its energy is less. What is the reason for the stability? That is a question. So another college has less interactions in triplet state. Another college says triplet state higher energy state. That is definitely not, because triplet state is actually lower. If you look at the energy diagram, triplet state energy is placed below the singlet. Another college writes when the spin changes, energy is lost, so triplet is less energetic and stable. Okay, and another college writes spin changes results in energy expenditure, so less energy in triplet state. Okay, so now come to the board. So this is the ground state. When it goes to an excited state, assume that the initial state is like this. We are not going to designate it as either singlet or triplet. This much energy is given. Now we separately calculate what happens in a singlet and triplet. Singlet is this a case. Spins are paired but orbitally separated. In this case, spins are parallel. Now what happens when electrons are opposite in spin and parallel in spin? There is something called exchange energy, which means, or you can calculate the energy associated when this electron wave functions. Now we are going to use the language of quantum mechanics, because we know electron is both particle and wave. Assume that the wavy nature or the wave function, the representation of this particular electron interacts with the wave function of this electron. These interactions between these electrons will be different in this case and in this case. When they interact each other, because the spins are opposite, they can come close. Pauli's exclusion principle allows that. In this case, they are parallel spins, they cannot come close. So in general, when these two wave functions interact, which one will interact more? Definitely this will interact more, because they are allowed to come close, their spins are opposite. Now remember, both are electron, so they have negative charges. When two charges come close, what will happen to the repulsion energy? It increases. Whereas in this case, they are not come that close because they are parallel spins. So because of this interaction energy, in the case of singlet, this will shoots up because they are same energy, they are coming close. Triplet, equally it goes down. So that's why we have a triplet state here, we have a singlet state always up. So actually you are seeing this part of the Jablonski diagram. You have an S0 and an S1 and in between T1. So the real reason is the interaction between these electrons, which is having opposite spin and parallel spin. Opposite spin, when they interact, the repulsion energy is high because they come close. That's the answer for that. Now let us go back to the slide. Okay, so what are the time scales of absorption associate process? Suppose light is falling on a matter. How much time it requires for absorption? Let us think about the time scales. And once the absorption happens, you know that the system goes to the excited state. How much time it stays there? How much time it takes for this crossing from singlet to triplet? What is your general idea about these things? How much you know from reading some other books or journals or hearing some professors' classes? What is your idea about the time scales? So have a quick discussion about your peers and then I will come back to you. So one college says 10 to the power of minus 8 seconds. It's a shorter time, but that's not the correct answer. It is much shorter or much faster time scale of light absorption. BEC?
10 raised to minus 16 seconds.
Very close. So minus 6 minus. What is the answer? Tell me again.
Ten raised to minus 16 seconds.
Okay, so the right answer is 10 to the power of 15 seconds. So it's a 1 femtosecond time scale, 10 to the power of minus 15. So that short time is required when a light interact with the electronic system and then exchange the energy. In short, it's a very fast process. Okay, and then how much time it stays in S1, the singlet state? Can any college tell how much time it stays in the singlet state? One college already told femtosecond. Yeah, that's correct answer for absorption. So the light absorption time scale is already out. It's femtosecond, 10 to the power of minus 15 seconds. How much time it requires for emission? For example, fluorescence is one type of emission. What is the time scale for emission? So the question is how much time is required for a fluorescent molecule to come back to the ground state from the first singlet state. I am repeating the question, how much time it takes for a fluorophore to come back to the ground state from its first excited singlet state. VEC, can you hear me?
So 10 raised to the power minus 18 seconds.
So that leads to a very interesting question. We have told that 10 to the power of minus 15 seconds for light absorption, and 10 to the power of minus 18 is a shorter time. That is less likely, right? It could be higher than that of 10 to the power of minus 15, which means that it has to first absorb and then emit. The emission cannot be faster than absorption. First it has to get absorbed. So that takes 10 to the power of minus 15 seconds. So the answer will be less 10 to the power of below 15 number. So you want to try another answer?
10 raised to minus 11.
Okay. So now at least logically it is correct. I will tell you the correct answers. So this is the person. The slide you have seen the Jablonski's photo. He was from Poland. He looks like a army person. In fact, he was an army person. He participated in World War I and World War II, and in addition did lot of physics and chemistry. So Alexander Jablonski suggested this diagram. We are seeing again S0, S1, S2 and the right hand side on the T1. These are the time scales. So light absorption is femtosecond. Emission, that means fluorescence, from S1 to S0, it is 10 to the power of minus 9 to 10 to the power of minus 10 seconds. Very close. Student says minus 11. Now phosphorescence. Phosphorescence is a slow process. It takes longer time, 10 to the power of minus 6. Sometimes that's microseconds or even seconds, depends upon the system. Now this intersystem crossing from S to T, it takes 10 to the power of minus 12 seconds. So in this Jablonski diagram, you are seeing two types of arrows. One is straight line arrows going up, going down, and there are wavy arrows. These are all wavy arrows, right? So that represent two different types of processes. The straight lines involves either light absorption or light emission, whereas wavy lines indicates energy lost by heat. Okay, so as you can see that it can get excited into a higher energy called S2, but immediately after it is losing its energy and come to S1. From S1 it jumps to S0 by emitting a photon. So this transition from S2 to S1, there is no photon, there is no light emission. This energy is radiation-less transition. That means it is heat given out. From here, it emits light. Similarly, when it goes from S to T, no light is emitted, only heat is given out, and from this T, it comes back and emitted light by light emission, that's called phosphorescence. And phosphorescence is always higher than fluorescence, I mean slower than fluorescence, because the spin has to again change before coming back to the ground state. So phosphorescence is a slow process. So and this is called Jablonski diagram. So any student who wants to study the basic of photophysical aspects, Jablonski diagram is the most fundamental aspect in photophysical chemistry. So the whole process of Jablonski diagram is like this. Matter absorb light, it goes to the electronic excited state, appropriate energy if it is given. For example, yesterday we learned UV and visible. This energy will take the matter to its electronically excited states, and from electronic excited state energy is dissipated. How energy is given out? Two different ways. One mechanism is called radiative mechanism, another one is called non-radiative mechanism. In non-radiative mechanism, there are two different types. One is chemical, one is physical. In fact, in the Jablonski diagram, we have seen only physical process. We call it inter-system crossing, and another one is internal conversion. Internal conversion is the one from S2 to S1. Inter-system crossing is from singlet to triplet. Chemical process can also happen either from S1 or T1 when it starts reacting, called photochemical reactions. So when you excite electronically, from the excited state, the molecules can react, and upon reaction, then there is no light coming back, that energy is lost non-radiative pathway, that's called chemical. Now radiative mechanism, there are two processes, we already seen that, fluorescence and phosphorescence. What happens in this non-radiative mechanism? If it is a physical process, what is the net effect? Inter-system crossing or internal conversion, the wavy line which represents loss of energy in terms of heat. So the net effect is light energy is converted to heat energy, that's all. Whereas in this chemical process, what is the net effect? Light resulted in photochemistry. So there will be some reaction happening from singlet or triplet because it's at higher energy. So reaction happens. So the net effect is light is converted to chemistry. Whereas in this case of fluorescence or phosphorescence, the net effect is that light will be converted to another form of light. You give light, it absorbs, it also gives you back the light, but not necessarily the same amount of or the same energy of the light that is absorbed. So that's why I put light dash here. So these are the whole processes of photophysical processes when an organic molecule absorb energy from radiation, especially UV visible. Now if you provide some other type of energy, for example microwave energy or infrared radiation, these are all electromagnetic radiations, right? So when you provide that, won't you think that there will be absorption of light? Or in other words, what is your understanding that suppose I am putting infrared light instead of UV light, whether matter can absorb that and any change happens to the electronic energy, or I can give microwave, what will happen to the energy of the electron? UV visible, just now we have told there will be electronic excitation, from S0 to S1 it jumps, and quantum chemistry or quantum physics, quantum mechanics already told that the energy levels are quantized. So any movement, any energy associated with the molecule will have discrete energy levels. What we have seen in this slide is what will happen when UV or visible light falls on matter. Assume that you are allowing infrared radiation to fall on matter. What energy change it can cause? Or assume that you are giving microwave radiation. What change it can happen? Will get affected. Yesterday we talked about different types of energy associated with a molecular system, and when you use UV visible, just now you have seen that electronic energy is getting affected. Okay, so let us quickly go to the board again, 1 second. So this diagram we have drawn yesterday. This is energy on this y-axis. As we said, there are different types of energy associated with molecular systems. For example, there are electronic energies, vibrational energies, rotational energies, translational energies, nuclear energy. These are all energies associated with the systems. Now if you look at the energies of these different systems, how they are related to each other, that information is needed to answer that question. I am representing S0, the electronic energy level. This is S1, this is S2. In between you can see several lines. S0 has several lines, S1 has several lines, S2 has several lines. These lines represents vibrational energy levels. Okay. Now in between vibrational energy levels, if you can zoom them, you will see that there are several discrete lines between each of these vibration energy levels. They are called rotational energy levels. So what does it mean is that to have a molecular rotation, you need very minimum energy. To have a vibration, molecular vibration, you need a little bit more energy. To have an electronic transition jump between electronic levels, you need much more energy. Now you can tell me, when we say UV visible falls on matter, we told that there can be an electronic transition. So when we use IR, what transition can be possible? IR energy and UV visible energy. You can simply compare it and then tell the answer. So chat is blinking, let us see. IR change in vibration energy levels, microwave rotational changes, and IR makes both vibration rotation changes. Yeah, so these answers are correct. IR is basically changing the vibrational energies of a system, and microwave changes the rotational energy level. So as you see the energies of this one, IR is having lesser energy than UV visible and microwave is having lesser energy than IR. So correspondingly it changes the energy levels. So when you talk about, yesterday we talked about absorption, today we are talking about emission. So in both cases there is something called mirror image rule. This is that rule. In that spectrum, as you can see, on your left hand side the blue line is calling absorption and the red one is called emission. It is as if like there is a mirror in between. Absorption is exactly, or the emission is exactly a mirror image of absorption. The question is, why such a thing happen? What could be the reason for a mirror image? You can again come back to this Jablonski diagram. There is S0, there is S1. In S0 there are different vibration energy levels, V0, V1, V2. S1 also there are different vibration energy levels, V0, V1, V2. I would have written V dash 0, V dash 1, V dash 2, just to distinguish between vibration energy levels in the ground state. Now the blue lines are absorptions, red lines are emission. Absorption is possible from S0 to all the vibration energy levels of S1, and emission is possible from the ground state, so the lowest energy state of the S1 to all possible vibration energy levels of the ground state. So in other words, as long as there is discrete vibrational energy levels, you can have several absorptions and several emissions. That's why it is structured. Yesterday we talked about that, why some spectra is structured, why some spectra is broad. The answer is that each of these small peak is for a particular transition to the vibrational energy level. It's also called vibronic transitions. Okay. Now if you compare the probability of transition of 0 to 2, so this is the 0 vibration energy level, this is second. So if you compare the probability of 0 to 2 transition and the probability of 0 to 2 emission, it turns out that these two probabilities are equal. You can ask me why it is equal. I have an answer, but it turns out that this absorption and this emission, there is a 1:1 correspondence between 0 to 2 absorption, 0 to 2 emission. Similarly 0 to 1 absorption, 0 to 1 emission, or 0 to 3, 0 to 3. In other words, whatever there is an absorption in this one, the same probability of transition exists for the corresponding emission. That is the reason why when this particular transition having high intensity, the corresponding transition will of the emission will also have equal intensity. So that's why the reason for there is a mirror image rule. This is a different transition, the same probability of transition will for this exist for this emission. And there can be some exceptional cases for mirror image, some cases it breaks. These are some examples, but there are reasons why mirror image rules. Many of the organic compounds exhibit this type of a mirror image rule. Now, this is a very important rule in photochemistry, it is called Cash's rule. I will show you a diagram S0, S1, S2, S3. You can see the transition from S0 to S1, S0 to S2, S0 to S3. This wavy line is called the energy dissipation by heat, and it's emit from S1 to S0. Now the question is, why it always come back from S1 to S0? Why not it start from S2 to S0? Why it is not coming from S3 to S0? So I want you to, you know the answer because the answer is already discussed. I want you to recollect those slides and then tell me the answer. Why always emission is coming from S1? Take a couple of minutes, talk to each other. Question is, why the emission is always from S1 to S0? Why can't it emit from S2 to S0, S3 to S0? Yeah.
First interconversion, next intra-system conversion, intra-system crossing.
Yeah, your answer
Always
is very
electrons
clear.
are trying to approach near
Yes.
energy.
Yeah. Okay. So I will take that answer. I will slightly modify it.
Hello?
Close that. Yeah, I think the answer is almost correct. So what happened is that in the Jablonski diagram, if you look at the Jablonski diagram where we talked about the time scales, different time scale, light absorption, internal conversion, inter-system crossing and fluorescence. If you remember the time scales properly, you can answer this question. Light absorption is very fast, we said femtosecond. This internal conversion or inter-system crossing, any wavy line is 10 to the power of -11 to -13 or -14 seconds. That is the next fast process. And then fluorescence is 10 to the power of -9. That's a relatively, so among these three actions shown in this slide, fluorescence is the slowest process. So what happens, the moment you excite to S2 or S3, they immediately come back to S1 because this kinetics, this process is very fast. So once it comes back to S1, then the white is coming back because as you see in the figure, S1, S2, S3 are closely spaced compared to S0 and S1. So because of the closeness, they immediately dissipate the energy in the form of heat and then come to S1 and they stop because there is a large difference in the energy. Then from then S1 to S0 it emits light and come. So that's the reason why it doesn't matter where you excite, S0 to S1 or S0 to S2 or S0 to S3, you always get emission from S1 to S0. This important rule is called Cash's rule. Emission is independent of excitation wavelength. That's called Cash's rule. So you can excite either to S0 to S1 or put more energy S0 to S2 or again more energy S0 to S3. It doesn't matter, they will come back, everything come back to S1 and then it emits. So emission becomes independent of the excitation wavelength. Once you excite, there are two different phenomena we need to think about. These are all important for you to develop a sensor based on fluorescence. Without understanding the basic concepts, no engineer can work out on a model. So what happens when you have fluorophore, if you excite it, sometimes a loosely bound complex can form in the excited state. A fluorophore A can form a complex with the fluorophore A itself, that's called excimer, which means excited state dimer. A fluorophore A can form a complex with the B, which may or may not be a fluorophore. So AB type of complex, which is called exciplex or excited state complex. So either excited state dimer or excited state complex can form in the excited state. They are loosely bound complex. The loosely bound means there is no covalent bond formation. There will be some non-covalent interactions between A and A or A and B. Now I want you to predict the shift in emission wavelength of excimer or exciplex compared to that of corresponding monomer. You want only high school chemistry or physics knowledge to answer these questions. Just recollect what way the emission, suppose excimer and Xc plus are emitting, what way the emission spectra will shift compared to the monomer emission. So we have A, you are exciting it, it forming AA. So the emission of AA will be different from A. In what direction AA will be, emission will be shifted? Either it is higher wavelength or lower wavelength. What could be the reason for that? Think about the question, I will come back to you in a minute. So VECAP college says it will shift to lower wavelength. Now you need to give a justification for that. We will come to you. Let us see some other colleges give their opinion. One college says either low or high. Pick up one side. You say either low wavelength or higher energy. I want you to pick up one answer because mostly it is one way it will be shifting as a result of excimer formation. If it forms a aggregation or a long range order, your answer is correct. It can be shifting to either low energy or higher energy. But for a dimer, it mostly it will be one way it will be shifting. So only two colleges give the answer. We'll go to the right. Your answer is your reasoning is correct, but answer is wrong. See, you said bond is something, some attraction is happening, right? So there is an interaction between two molecules in the excited state AA, and there is some attraction happens. Attraction always lower energy. You are right, but it is lowering the excited state energy. So what will happen to the energy gap? So in fluorescence spectroscopy, we talk about HOMO-LUMO gap. So initially, come to the board. We'll go to the board and then see. See, initially this was the situation. Okay, A going to the excited state, we normally represent by A star, and it emits. This is the normal fluorescence. Now suppose A and A forms. As you said, as you correctly said, it's attraction. So attraction brings energy to, energy decreases as a result of attraction. So energy of this excited state decreases. This is A star A, or more correctly A star, right? So now what happened to this energy? If it emits from the excimer to the ground state energy is not changing. Now the question was, compare this emission to this emission. Now it is clear this emission is less. If this emission is less, what will happen to the lambda? Energy and lambda are inversely proportional. E is equal to h nu hc by lambda. So energy decreases, lambda increases. So the answer is it will shift to higher wavelength. Okay, so there is something called quantum yield. I am going to go a bit fast here. Quantum yield is a process of basically the definition of quantum yield is number of photons emitted to the number of photon absorbed, and the maximum value for quantum yield is 1, because if a system absorbs 10 photons, it can emit 10 photons, it cannot emit 11 photons. So the ratio, maximum ratio you can take for quantum yield is 1. But quantum yield of a photochemical reaction, it can have maximum value more than 1. That's an interesting aspect. For example, take the case here, hydrogen iodide is decomposed in presence of a heat radiation, light radiation. It forms H dot I dot. What happens? Another one I dot will interact with another hydrogen iodide molecule. Again, it decomposes, and this is a termination step. So in this whole process, you use one photon, but decompose two hydrogen iodide molecules. So in such cases, quantum yield value can be more than 1. Number of molecules changed in a particular way by photons absorbed. Only one photon absorbed, two molecules changed. So the quantum yield of photochemical reaction in this case is 2. Quantum yield of a photochemical reaction can have maximum value more than 1, whereas quantum yield for a photophysical process, that means the Jablonski diagram, the maximum value is always 1. Okay, very another interesting topic that you need to discuss before you go for a sensor based on fluorescence. It's called fluorescence lifetime. I am going to give you a statement and you need to explain me what you understand by that statement. The statement is here. The excited state lifetime of anthracene is 5 nanoseconds. What does you understand from the above statement? Okay, that's the answer for the previous one, higher wavelength. It is a time it stays in the excited state, not complete. PSGCT. That definition is not complete. VCAP writes conjugation. I am not getting the meaning of that. Of course, anthracene is a conjugated molecule. But what do you mean by 5 nanosecond is its excited state lifetime? One college, most of the students think that way. It is a time that it stays in the excited state. But we are going to see that that is not the correct definition. So there is a general feeling that when we say lifetime a value, it is a time that the molecule stays in the excited state. So let us take a hypothetical situation. I have 10 anthracene molecule. I am exciting it. It goes to excited state, 10 molecules. Now after 5 nanoseconds, what will happen? According to your definition, all the 10 anthracene molecules are in the ground state. But that's not correct. Even after 5 nanoseconds, some molecules will be there in the excited state. That is true for any organic fluorophore or any molecule in the excited state. So the lifetime is a bit more tricky concept than the number that conveys you. It can be 5 nanosecond, 10 nanosecond or 100 nanosecond, but it doesn't mean that by that time all the molecules are coming down. It actually connects with the uncertainty principle, Heisenberg uncertainty principle. When you measure these properties, there is a hidden uncertainty in measurement. So what they do is, so we cannot actually precisely calculate or determine experimentally the lifetime and its energy. It's like position and momentum in quantum mechanics. There will be always an uncertainty in either of these things. They are called conjugate variables. So here energy and time, they are conjugate variables. You cannot measure the exact time very precisely. If you measure that precisely, then the associated energy calculation will be very much erratic. So what they define this excited energy is the average time that a molecule spends in its excited state. More precisely, 66% of molecules will come back by this time. For example, if you excite anthracene, 66% of the amount of the anthracene excited will come down by 5 nanoseconds. But the other 33, 66.666, 33.333, that's the distribution. So the remaining 33.333% can come even after 5 nanoseconds. It's a probability of emission. So that is the real meaning of excited state lifetime. So it's an average time that a fluorophore stays in the excited state, and this is a direct consequence of uncertainty principle. Now there are two important instruments you need to familiarize as far as fluorescence is concerned. One is called steady state fluorimeter or fluorometer, and another one is called time correlated single photon counting. I will briefly tell what the difference it is. This is the steady state spectrofluorometer, where as you can see there is a light source and it comes. This part is the monochromator. Yesterday we have seen the monochromator and the UV visible. It contains some lenses and a grating. The idea is that when a light source gives all sorts of wavelength, the grating will separate based on the principle of a prism. It takes some of the wavelength and you can select the wavelength which is going to the sample. Here is your sample. So it comes probably 200 to all the way to 800 nanometer, but you can selectively take 350 nanometer using this monochromator, and 350 is coming and falling on your sample. 90 degree you are collecting the emitted light. So one question is, why 90 degree? Why can you put the light coming out from here? It is possible. So when the sample absorbs this light, it goes to the S1 state or S2 state, it come back to the S1 and emits, and the emission is 360 degree. It emits all the direction. Why we collect in the 90 degree? That is just to avoid this beam, the excitation beam. So when you have putting light in this direction, that light will be going through here. Some light will be absorbed as we know, remaining light will be going through in the direction, right. So to avoid this direction of this excitation beam, you collect emission light from 90 degree. It goes to another monochromator and correspondingly you can choose the wavelength, it goes to a detector. Now in this case lamp is always on, that is why it is called steady state emission. You are getting an excited state S1 here with the concentration steady. Why? Because light source is always on. So keep on pumping the light, molecule start absorbing, it goes to excited state, simultaneously it comes back, again absorbs. So after some time there will be a steady state concentration of the S1 and the emission is getting from S1, you record it. So this instrumentation is called spectrofluorometer. Time correlated single photon counting is a bit more tricky instrument. Here again there is a light source, light pulses are coming, it is not continuous, the light is not complete, the source is not always on, it is a pulsed light. So light pulses are coming out, here is your sample, it absorbs the pulse, it emits the light, it goes to the monochromator system and then it reaches detector. Now this emission is coming from the sample and we know that this emission is a time dependent phenomena. Lifetime is 5 nanosecond, means some molecule will emit at the 1 nanosecond, some molecule may come out 2 nanosecond, 66% will come before 5 nanosecond, that is true. So how do we find out the time? There is something called time amplitude converter and digital analog converter. What this box does is, when this light source start a pulse, it gives a voltage which is taken into account when at the beginning of the process. It comes to here, sample absorb, sample emits, it reaches through the PMT. At that time it gives another signal, stop signal. So there is a start signal, stop signal. The difference between the start and the stop, that is the time taken by the whole process, okay. That time you see here, you can convert that signal into time. Once you convert this into time, you will see that for 1 nanosecond there is this much emission happens. In some other cases, for example 2 nanosecond, more counts are there, more light comes to the PMT, photomultiplier tube, so more intensity, and 5 nanosecond probably somewhere here, 6 nanosecond also it emits, 7 nanosecond it emits, 10 nanosecond also it emits, but the counts are very less. So basically you are generating a probability distribution. By fitting this probability distribution you get the lifetime or you get the average time. So when you fit this decay trace, you may get 5 nanoseconds as a result, and that is called the average lifetime of any fluorophore. So this particular instrument, time correlated single photon counting, is used to measure the lifetime of the sample. The previous one is to measure the steady state emission spectra of the sample. With these two instruments you can think of probably developing some sensors. How do you make sensor? To answer this question, you need to understand this phenomena called fluorescence quenching. Any phenomena results in the decrease of fluorescence intensity or lifetime is called a quenching process. So you have a fluorophore, it gives you some intensity of light emission or it gives a certain value of lifetime, say for example 5 nanosecond. The moment you add an analyte, emission intensity decreases, lifetime value changes, and this phenomena is called quenching. There are two different types of quenching, one is called static, another one is called dynamic. The only difference is that static quenching, the fluorophore and the other substance interact in the ground state, is called static quenching, whereas in the case of dynamic quenching, the fluorophore is in the excited state, the other substance is in the ground state. So anything happens to the fluorophore in the excited state, it is called dynamic quenching. Anything happens in the ground state, it is called static quenching. Now the question comes to you, how do you distinguish between static and dynamic quenching? You want the definition of static and dynamic quenching again? This is a definition. If the emission quenching happens due to the interaction of fluorophore and the another species in the ground state, it is called static quenching. If the interaction is happening in the excited state, it is called dynamic quenching. That is the only difference. Now the question is, how do you distinguish between static and dynamic quenching? Right. So the question is, what way we can distinguish So we don't know whether it is strong or weak for static and dynamic. So it depends upon how the fluorophore and the other substance. So there is an analyte you are adding to the system, and as a result fluorescence intensity is changing, lifetimes can change, many things can happen. So if the analyte is interacting with the fluorophore in the ground state, the emission get affected. That is called static quenching. So sometimes analyte can interact with the fluorophore in the excited state. That is called dynamic quenching. So the question is, experimentally how do you distinguish color change? So some college says color change may happen. BSAR says using Sternwarmer plot we can distinguish. Okay, so that answer I will take. It is possible to distinguish Sternwarmer, but how? That is a question. Even we don't go to the technical terms like Sternwarmer, we can still say the answer from the slides we have discussed. So PSGCT says color change. Color change can happen. In which case? So let us go to the board. Static and dynamic. So the only difference is, as we said, the fluorophore and other substance. Let us call it Q. Q stands for quencher. It leads to a quenching of emission, right? So fluorophore and quencher, if it forms a complex in the ground state, it interacts in the ground state, that leads to emission quenching. It is called static quenching. Whereas goes to excited state, right, and then quencher interacts, that leads to a emission quenching. Suppose it is coming back, but it is not coming back. As a result of this interaction, this process is getting affected. This type of quenching is called dynamic quenching. Anything happens in the excited state. Anything happens in the ground state is called static quenching. The question is, how do you distinguish these two? Somebody is there on the chat. Now it says color change in dynamic case. See, color change can happen, but what happened is that here also color can change. Some complex is formed. So when complex formation happens, color change is also possible. So color change may not be the right way to distinguish them. The ideal way is, as we have seen two different instruments. One is a steady state fluorometer, another one is a time correlated single photon counting. One measures the emission intensity, one measures the lifetime. So one instrument will give you the intensity of the emission, intensity versus lambda. Another one is intensity as a function of time, that is called lifetime. So you get an exponential decay. By fitting that one, you get the lifetime. Lifetime we defined as the average time it exists in the excited state. 5 nanosecond means 66.66% of the anthracene molecule stays there for 5 nanosecond, right? So this is talking only about excited state. So if dynamic quenching is happening, obviously intensity will decrease due to any quenching, because quenching is the process which reduces the emission density. But imagine a case where only static quenching is happening. Okay, that means something is interacting with the fluorophore in the ground state, but still some fluorophore are going in the excited state. You are measuring the lifetime. Lifetime will not change because nothing is interacting with the excited state. So instead of 10 molecule, you may be exciting probably 5 molecule, because remaining will form a complex, or remaining may not be excited, but this 5 molecules 66% will come down with that same lifetime. So lifetime is an intrinsic property. Anything happen in the ground state will not affect the excited state lifetime of the species. So if you have only static quenching happening, lifetime will not get affected. In other words, you measure the lifetime of a fluorophore alone, you add a quencher into that or another substance, analyte to that, take again the lifetime, If you get the same lifetime, for example 5 nanosecond for anthracene, in presence and absence of any external species, you can coolly say that no dynamic quenching is happening. So that is one way of distinguishing dynamic quenching to static quenching. There are a number of ways. Probably another way that you can think from this diagram, I leave it to you, probably we can discuss tomorrow. One more way you can easily distinguish static quenching from dynamic quenching. But this differentiation between static and dynamic is important, because unless you know the mechanism of quenching, you cannot develop a sensor. So this fundamental information about how the fluorescence intensity is decreasing in presence of an analyte is important. That is why we are discussing here. And there can be many reasons for quenching. It can be simple collisions leading to energy loss by non-radiative pathway, electron transfer, energy transfer, solvent interactions, aggregation, excimer formation, Xc plus formation. So anything happens in the excited state can lead to a quenching. Just now we saw anything happen in the ground state can also lead to emission quenching, static quenching. So there are n number of reasons why the emission of a fluorophore can be quenched. Now the remaining 10-15 minutes, I would like you to ask questions on whatever you have learned, because the remaining part of this short course is to develop sensors based on fluorescence, which I think it is impossible for the 10 minutes duration remaining. We need more time. So we have one more class tomorrow. We will focus on that tomorrow, but remaining time I invite you to ask questions. I can give you the last slide, which is, why don't you write this one? I want you to write down these two aspects from this class. One aspect which is very clear and one aspect which is completely unclear. Yeah.
Ultraviolet spectroscopy is sometimes also called electronic spectroscopy.
Right.
What is the reason behind?
What is the?
What is the reason? मतलब कि जो ultraviolet spectroscopy is also called electronic spectroscopy. What is the reason behind it?
Yeah. So the reason is ultraviolet results in electronic excitation. When a species absorbs the light, ultraviolet light, we discussed about different types of excitations, right? Electronic, vibrational, rotational. So when UV light is absorbed, the system is, or the electron is getting excited electronically. It moves from one lower electronic energy level to higher electronic energy level. That's why it's called electronic spectroscopy. So there is a question on why there is a 90-degree in that spectrophotometer. That answer is, why there is an excited state, I mean why this configuration. The answer is very simple, because if you put the detector, we'll go to the board for a minute, in the sample chamber of the steady state fluorimeter, light is coming from here and the emitted light is collected in 90-degree. Why is that? Because if I put the detector here, then the emission light will come, on the top excitation light will also come, because here is my sample. The sample will not absorb the complete light of excitation beam. Some light will be passing through it. So to avoid these two lights falling on the detector is placed 90-degree. That's only reason. Another question, please explain the quantum yield. So quantum yield is basically efficiency. You give some photons to a system, some photons are absorbed, and as a result some photons are emitted also after some time. So it's a ratio, emitted versus absorbed. If I am getting a value of 1, which means that all the absorbed are emitted. If I am getting 0.5, which means that only 50% of the absorbed is getting emitted. It basically tells you an efficiency of a process. Another question, why the emission is collected at 90-degree? Yeah, that is what we just answered. Quantum yield was another question. Other unclear aspects? So that means the sensor technology. That means suppose I have toxic metal A, B, C and D in the system. I am going with a sensor. The principle is very simple. My sensor will bind only with A, and if it binds, it gives a color difference. So I am going with a sensor, I am adding it, or I am taking the sample and then adding it to the sensor. If it contains the toxic element A, then only it will bind and then only it will change the color. If there is B and C and D, it won't change. So I am designing a system in such a way that there is a specific interaction. So in that particular example yesterday we discussed, it has single strand DNA interacting with the mercury only. Other metal ions also slightly interact, but it won't give that very drastic change. So only mercury is there, it interacts. As a result of interaction, color changes. So then I can conclude that color is changing, there is some interaction, and this interaction is due to this particular toxic metal ion. Plasma spectroscopy we can use, but that use or application is very limited. Most of the spectroscopic techniques that you are seeing is using this electromagnetic radiation, because it's basically defined as the interaction between the radiation and the matter. So the electromagnetic spectrum, see molecule can be electronically excited by thermally also. If you can give that much energy by any other means, not necessarily thermal but by electrical discharge or any other arc, it can electronically excite. The spectroscopy usually referred to as the study of interaction between radiation and matter. So the whole spectrum of electromagnetic radiation, starting from gamma rays, radio waves, right, and then the visible, UV visible, IR, microwave, X-ray, so many electromagnetic radiations are there. These radiations, when they interact with the matter, energy exchange can happen, and as a result you can conclude some useful information about the structure of the matter, and since structure is connected with the property, you can use this information for developing sensors. That was the topic of discussion. Please explain excimer and Xc plus. Okay, that is very simple. When a fluorophore, for example A, is absorbing light, it goes to the excited state. Okay, it form a complex with another A which is in the ground state. So we will have A star and A interaction. So it's like AA or a dimer. So in the case of, only thing is that one of these A's is in the excited state. So it's called excited state dimer or excimer. Suppose you have A and B, two different species, that can also form complex in the excited state. A star will form a complex with the B. Then it is called excited state complex or Xc plus. The only difference between Xc plus and excimer is, Xc plus it is A and B, excimer it is A and A. Both are forming complexes in the excited state. 4-5. Okay, so now it is time. We will wind up today. We will see you tomorrow at 2 o'clock.